In the realm of modern warfare, few machines command awe quite like the advanced fighter jet. These are not merely aircraft, they are precision instruments, sculpted from cutting-edge materials, packed with sophisticated electronics, and propelled by immense power. Each one represents billions in research and development, culminating in a price tag that can easily reach hundreds of millions of dollars. A single operational unit is a marvel, designed to operate at the very limits of human and mechanical endurance, a guardian of the skies, a symbol of national technological prowess. Its loss, under any circumstances, is a significant blow, a multi-million-dollar void in a nation's defense capability. Yet, even these titans of the sky, meticulously designed and rigorously tested, are not immune to catastrophic failure. High above the earth, a mission underway, the unthinkable can occur. A sudden, violent shudder, a loss of control, a cascade of warning lights, and then, silence, replaced only by the roar of the wind as gravity reclaims its domain. The sleek, formidable machine, once a symbol of power, now becomes a rapidly descending object, heading towards an inevitable impact. The sheer scale of such a loss is staggering, a multi-million-dollar asset disintegrating in moments, all without a shot fired by an adversary. But what could cause such an unprovoked, absolute breakdown? The answer, in this particular instance, was not an act of enemy aggression, nor a complex system-wide malfunction. It wasn't a software glitch, a sophisticated cyber attack, or a high-velocity mid-air collision. The culprit, discovered only after a painstaking, months-long investigation, was a tiny, seemingly insignificant piece of hardware. A single screw. A common, industrial component, likely mass-produced, costing perhaps $1, if that, to manufacture. How could such an infinitesimal part, so basic in its design and purpose, bring down an engineering marvel worth hundreds of millions? It's a paradox that continues to challenge our understanding of complex systems and the crucial role of every detail. Fasteners like screws, bolts, and rivets are the unsung heroes of engineering. They hold our world together, from the spectacles on our nose to the skyscrapers that pierce the clouds. In an aircraft, their importance is magnified exponentially. Every single screw, bolt, and rivet is specified for a precise application, subjected to specific loads, and designed to withstand particular environmental stresses. There are tens of thousands of them in a modern fighter jet, each with a designated role, from securing a tiny sensor to bearing significant structural loads. They are the silent, constant guardians ensuring the integrity and functionality of every subsystem, every component, every joint. This particular screw was not just any fastener. It was situated within a highly critical system, a vital artery in the jet's operational physiology. While the exact system can vary across different incidents, the principle remains constant. It was responsible for securing a component essential for flight control, engine performance, or perhaps a primary structural element. Imagine it connecting a hydraulic line vital for rudder movement, or securing a sensor that feeds crucial data to the flight computer, or even anchoring a vibration dampener on an engine. Its position might have seemed innocuous, hidden away in a complex assembly, but its function was absolutely non-negotiable for safe flight. Even a simple screw is a product of complex manufacturing and metallurgical science. The type of metal, its heat treatment, the threading process, and protective coatings are all precisely chosen to meet rigorous aerospace standards. A seemingly minor deviation in any of these steps, an impurity in the metal, an incorrect hardening process, or an imperfection in the thread, can compromise its integrity. For aerospace-grade fasteners, tolerances are incredibly tight, and quality control procedures are exhaustive, designed to catch even microscopic flaws. The assumption is that every single component, no matter its size or apparent simplicity, meets these exacting specifications. Once manufactured, these components are integrated into the aircraft during assembly. This process involves thousands of individual steps, often performed by highly skilled technicians following incredibly detailed instructions. Every screw has a specified torque value, how tightly it must be fastened. Too loose, and it might vibrate free; too tight, and it could strip the threads or overstress the material, causing microfractures. In a machine with millions of parts, relying on human hands and calibrated tools, the potential for error, however small, is ever present. A momentary lapse in concentration, a miscalibrated tool, or even the wrong screw from a batch can set a catastrophic chain in motion. Fighter jets operate in an environment of extreme stress. They endure violent maneuvers, supersonic speeds, and the constant, intense vibrations emanating from powerful jet engines. Over time, these forces take their toll. Even perfectly manufactured and installed components can succumb to fatigue. Metal fatigues not from a single, overwhelming force, but from repeated cycles of stress and relaxation. Microscopic cracks can form and propagate, growing slowly until the material's structural integrity is compromised. For a critical screw, this means a gradual weakening, a silent countdown until the point of ultimate failure, often undetected until it's too late. On that fateful flight, the confluence of these factors reached its critical peak. Perhaps the screw had been slightly over-torqued during installation, creating an initial weakness. Or maybe it contained an inherent material flaw missed by inspections. Combined with the relentless assault of flight stresses and vibrations, that tiny defect began to propagate. In the air, the screw finally gave way. This was not a slow unraveling, but a sudden, decisive fracture. The component it was securing, now unbound, immediately shifted, or detached, or ceased to function as intended. This single point of failure instantly compromised the integrity of its connected system. The failure of that one screw triggered an immediate and devastating chain reaction. If it secured a flight control surface, the aircraft's ability to maneuver would have been severely hampered or entirely lost. If it was part of an engine mount, the engine's stability could be compromised, leading to thrust imbalance or even detachment. Data from sensors, crucial for the flight computer's operations, could become erratic or cease altogether. In a modern fighter jet, systems are highly integrated. A failure in one critical area quickly impacts others, creating a cascade that rapidly spirals beyond the pilot's capacity to correct or compensate. The aircraft was no longer responding predictably. Imagine the scene inside the cockpit. What began as a routine flight quickly devolved into a terrifying struggle for survival. Alarms blared, indicators flashed red, and the controls became unresponsive or unpredictable. Pilots, trained for every conceivable emergency, would have fought valiantly against the failing machine, attempting to diagnose the problem and implement emergency procedures. But when a primary system, fundamental to flight, is compromised at its core by an unforeseen mechanical breakdown, even the most skilled aviators are helpless. The aircraft, once an extension of their will, became an uncontrollable, heavy mass, accelerating towards the unforgiving ground. The eventual impact was devastating. A multi-million-dollar testament to human ingenuity was reduced to scattered fragments across a wide area. The crash site would have been a scene of utter destruction, a stark reminder of the immense energies involved when a heavy object traveling at high speeds suddenly meets the Earth. Rescue and recovery teams would have converged, not only to search for survivors but also to secure the site and begin the arduous process of piecing together what happened. Every fragment, every scorched piece of metal, every bit of debris becomes a potential clue in the grim puzzle of understanding the final moments of the aircraft. The investigation that followed was a monumental task of forensic engineering. Teams of experts, from metallurgists to flight control specialists, converged on the crash site. Their mission, to meticulously collect every piece of wreckage, often down to the smallest shard, and reconstruct the aircraft to understand the sequence of events. The black boxes, the flight data recorder and cockpit voice recorder, would provide crucial insights into the aircraft's performance parameters and the pilot's final communications. But the physical evidence, the broken metal, tells an even deeper story, revealing the precise point of initiation for the catastrophic chain of failures. After weeks, perhaps months, of painstaking reconstruction and analysis, the investigators honed in on the specific area of failure. And there it was, a fracture, clean and sharp, on a small, unassuming screw. Its remnants, pulled from the twisted wreckage, told a clear story under the microscope. This wasn't corrosion, nor external damage. It was a failure from within, a fatigue fracture or a material defect amplified by stress. The revelation was both shocking and profoundly humbling, the demise of a multi-million-dollar technological marvel traced back to a single, dollar-priced component. The irony was almost unbearable for the engineers and designers involved. The question then shifted from what to why. Was it a manufacturing defect, a microscopic flaw introduced during its creation that went undetected through multiple layers of quality control? Was it an installation error, an improper torque applied by a technician, stressing the material beyond its limits from day one? Or was it a design oversight, where the stress calculations for that specific point were underestimated, leading to premature fatigue? These are the brutal questions that must be answered to prevent recurrence. Every detail of the screw's life cycle, from its raw material to its final installation, was scrutinized under intense pressure. The loss of the fighter jet itself, valued at $300 million, was just the beginning of the financial fallout. The investigation cost millions more, consuming countless hours of highly skilled labor. There were potential costs associated with pilot loss, though in many such incidents, pilots might eject. More broadly, the strategic impact on military readiness, the delay in future procurements, and the potential for a blow to national prestige all add to the ledger. This single screw's failure triggered a cascade of expenses and implications far exceeding the initial aircraft's value, underscoring that the cost of a cheap part can be astronomical. From such a devastating failure, profound lessons are invariably learned. Engineering protocols are reviewed and often completely overhauled. Quality control measures are tightened, sometimes to an almost obsessive degree. Training for technicians and inspectors is enhanced, emphasizing the criticality of every single component, no matter how small. The incident serves as a stark reminder that in complex, high-stakes environments like aerospace, there are no minor details. Every component, every procedure, every human action contributes to the overall safety and reliability of the system. Complacency, even in the smallest forms, can have truly catastrophic consequences. Following such an event, it's not uncommon for the affected part or even the entire subsystem to undergo significant redesign. Engineers might opt for a different material, a more robust fastening mechanism, or incorporate redundant systems where possible. If the failure was due to stress concentration, the geometry of surrounding parts might be altered. The aim is not just to fix the immediate problem but to ensure that such a failure mode cannot occur again, or if it does, that its impact is mitigated. The $1 screw becomes a catalyst for multi-million-dollar redesigns, reinforcing the principle that prevention is always vastly cheaper than cure. Beyond metallurgy and mechanics, this story highlights the persistent human element in engineering. Despite the advanced tools, sophisticated software, and stringent processes, humans design, build, inspect, and maintain these machines. Human error, whether a miscalculation in design, a slip in manufacturing, or an oversight during maintenance, remains a critical factor. It's a constant battle against complacency and the limitations of human perception. The incident is a poignant reminder that even in an age of automation, the vigilance and conscientiousness of individuals are paramount to the safety and success of ventures that push the boundaries of technology. This saga of the $1 screw and the $300 million fighter jet underscores a fundamental paradox of modern engineering: the greater the complexity and sophistication of a system, the more potential points of failure it may contain. And often, these critical points reside in the most unexpected, seemingly trivial components. The entire structure, built to withstand incredible forces, remains vulnerable to the fragility of its smallest parts. It's a delicate balance, a constant dance between innovation and reliability, where the pursuit of perfection is an endless, unforgiving journey, illuminated by the shadows of past failures. For every catastrophic failure that captures headlines, there are untold millions of successful flights, safe operations, and resilient systems. These are maintained by an army of unsung heroes, the engineers, technicians, quality inspectors, and maintainers who dedicate their careers to preventing precisely such incidents. They are the ones who learn from these mistakes, tirelessly refine processes, and obsess over details to ensure that the wonders of modern technology continue to serve us safely and effectively. The memory of failures like this one serves as a perpetual motivator, a grim reminder of the stakes involved, driving them towards an impossible, yet essential, goal of zero defects. The story of the $1 screw that crashed a $300 million fighter jet remains a timeless reminder, echoing across industries far beyond aviation. It's a powerful parable for anyone involved in design, manufacturing, or operations where precision and reliability are paramount. From medical devices to infrastructure, from software development to space exploration, the principle holds true: the integrity of the whole is only as strong as the integrity of its weakest part. It urges us to question assumptions, scrutinize the mundane, and never underestimate the profound impact of the seemingly insignificant. Because sometimes, the smallest component holds the power to unravel everything.